So one of the most common issues that riders tend to run into, and certainly something that kind of dominates the Reddit posts and concerns about starting a motorcycle, and right now as we get into the spring season, it's going to become more and more common that you're going to hear guys talk about the fact they can't start their bike, they don't know why, their battery looks charged, and trying to figure out why they can't get that bike going. So today we're going to talk about batteries, we're going to talk about different types of chargers, and we're going to show why you can't trust an open circuit voltage test on an AGM battery. And more importantly, I'm going to explain the chemical process that goes on inside your battery so that you have a better understanding of why your battery isn't working the way you think it should. Today we're covering batteries and the most common reasons why motorcycle batteries fail, but more importantly, ways to care for and test your motorcycle battery. As warmer weather starts rolling in, more riders will be down in the garage getting ready for another riding season. Unfortunately, the first time you start your bike after the winter break can result in disappointment as your battery just doesn't have the juice to light the fire of your two-wheel passion anymore. There are 3 different types of lead-acid batteries. The most common battery is called a flooded battery. That's because the electrolyte is in a fluid form and not in a suspension. These batteries are the least expensive to manufacture, but can require water top-ups to the electrolyte as they emit gases while charging and discharging. So that means also they can leak, especially in off-road conditions. They are also the most susceptible to failure due to vibration, and especially more so than our other 2 options. The next lead-acid battery is a gel battery. In these batteries, the electrolyte is suspended in a medium, typically silica. This does not act like a liquid, but as the name suggests, a gelatin. When a load is placed on the battery, ions travel through the medium and the plate separator that acts like a membrane. Gel batteries are resistant to vibration, are zero maintenance, and are known to discharge at deeper depths like flooded batteries do. Their disadvantages are they need to recharge slowly and can be damaged internally with heat. All batteries dislike extreme heat, but gel batteries can create voids in the electrolyte suspension from heat. For this reason, gel batteries must come off charge as soon as they're finished to prevent overheating. Gel batteries are also more costly to manufacture than our next option, the AGM. AGM batteries, or absorbent glass mat, suspend the electrolyte in fiberglass mesh. This mesh absorbs the electrolyte, as the name suggests, and holds it while allowing the chemical discharge and charge process to occur as it does in a flooded battery. AGMs have a lot of the same appealing features as gel batteries. They're zero maintenance, they don't emit any gas, they're spill-proof and of course very resistant to vibration. Plus, they're not susceptible to burn voids like a gel battery is. This is why AGM has become the staple in power sports for lead acid. The drawbacks of AGM are their limited depth of discharge. AGMs don't like being discharged beyond 60% of their capacity, or 40% left in the battery. Flooded and gel batteries are comfortable at 80% depths of discharge. AGMs are also prone to sulfation crystal buildup like a flooded battery, which we'll cover in detail later on in the video. The advantage of AGM is that it thrives under consistent charge, and this is the easiest way to care for your AGM through something called float charging. This is where a charger can supply just enough current to prevent sulfate crystals from building up on the cell plates. Both AGM and gel batteries are more expensive than flooded lead-acid batteries, but are typically half the cost of lithium-ion motorcycle batteries. Quickly here, I'll mention a little bit about lithium-ion batteries. Of course, they're also zero maintenance and do not sulfate like any of the lead-acid batteries we just talked about. This means they can be left to deeply discharge without damage and are restored quickly through fast charging. A lithium-ion battery only weighs 15 to 20% of that of its comparable lead-acid, and when they're available for your motorcycle or any other vehicle, it's worth considering as a strong option.
The only other thing that I'm going to mention here before we get started is that a lead-acid battery, whether they be gel or AGM or flooded, although they're an electrical storage system, the processes that are going on inside the battery are all chemical-based.
A battery doesn't store electricity. It stores the chemical energy necessary to produce electricity. When you apply a load to a lead-acid battery, it causes the sulfuric acid and water solution, otherwise known as electrolyte, to react on a chemical level with the lead oxide plates, or what are known as the positive cell plates, and the pure lead plates, which are the negative cell plates. The chemical reaction releases positively and negatively charged ions that produce the current your electrical system needs.
So the first thing we're going to do is test the battery. And the most common way that you do that is you grab your voltmeter, set it to DC volts, and we're using the scale of 20 here because it's only a 12 volt battery. And what we're going to do is run the open circuit test, and I'm going to show you what the readings are open circuit on this battery. And we're just going to hook it up, and we're going to see the voltage, which is about 13 volts, which in normal operations would be, although this is a little on the low end, not crazy low for a 12 volt battery. You got to remember that a 12 volt battery has 6 cells in it. Each one of those cells optimally produces 2.2 volts. So 13 volts total works out with the math. So we've tested our battery and we know what the voltage is. I'm going to go ahead and turn the bike on and try to start it. Okay, so the battery is a no-go. Yet, when we tested it, it showed over 13 volts. So what's the deal? Well, here's when we get into the anatomy of what is going on inside the individual battery cells.
A 12 volt battery is made up of 6 individual cells, which in turn is made up of positive and negative plates mentioned earlier. Cells always have odd numbered plate configurations, like 3, 5, 7, 9, and so on. In the cell, there's always one more negative plate than positive plate. These plates are connected to bus bars that span the top of the battery, connecting the negative plates to the negative terminal and the positive plate to the positive terminal. The positive and negative cell plates are also kept apart to prevent short circuiting, and they use a separator material, plastic typically in the case of flooded batteries, a membrane or a glass mat in gel batteries and AGMs, and also in the AGM the glass mat does double duty, holding the electrolyte in suspension and not allowing the positive and negative plates to come in physical contact with each other.
The foolproof method in testing a battery like this, you have to put it under load. And we're going to do that using the bike, and we'll see what happens with the voltage. So now we're going to run the load test on the battery. And what I've done here is I've charged up this faulty battery again. I put it on the charger and let it sit for about 30 minutes to try to put some additional charge back in it. And just to prove what a dramatic difference this makes. So we're going to go ahead and hook up our leads And we're going to see, in fact, we have about 13.3 volts in the battery, which, like I said, in most cases would mean we have a good battery. Now we're going to turn on the bike while holding our leads on the battery. And we see the voltage drop significantly all the way down to around 11. And this gauge is not showing, or this voltmeter isn't showing everything that's going on. In fact, the voltage is dropping, even more significantly than that. What's actually happening inside of the battery is that one of the cells has sulfated to the point where crystals have punctured from one plate to the other, and has shorted it out. Now we see that the voltage in the battery is dropped below 12. In most fuel-injected bikes, the ECM won't even fire the bike if you have voltage much below 12 volts in the battery.
When a load is placed on the battery, sulfate crystals form on the plates as a result of the chemical reaction that releases positively charged hydrogen ions and negatively charged sulfate ions. These crystals are dissolved back into the electrolyte when charging, provided, however, that the charging happens immediately after discharging. Repeated buildup of layers form structures that can block off the lead plates and prevent the battery's normal chemical reaction. Or they can build up so significantly that the separator is damaged and can no longer prevent the cell plates from shorting out. During storage of your motorcycle, there's always a small draw from your bike's electrical system. The clock on the dash, the alarm system, and other items can draw power continually. But even if your motorcycle doesn't have any electrical components drawing power, or you physically remove the battery from your bike, the chemical process is still continuing, and the battery naturally discharges at about 1% per day. This discharge also results in sulfate crystal buildup. If left uncharged for more than 30 days, the sulfate hardens, killing your battery. And this is why leaving your battery for extended periods is not a great idea. So what's the solution? AGM batteries need smart chargers that can maintain or float charge the battery, always supplying current needed to reverse the sulfation process buildup. Your motorcycle battery should be left on charge for at least 24 hours in every 30-day storage period. Or if you're using a maintainer style battery tender, just leave the battery on the tender and let it provide the consistent float charge voltage. When replacing your battery, it's important to charge up your new battery to a full charge before putting it in the bike. Ideally 24 hours of charging if possible. Although a good retailer of batteries will be rotating their stock to ensure that the battery never sits on the shelf for more than a few months at most, you also want to get the most out of your new battery. And a full charge before applying a load will help do that. When removing your old battery, always disconnect the negative cable first. The negative or ground cable should be the first one removed and the last one hooked up. This prevents the possibility of accidental grounding to the frame or any other metal components when disconnecting or reconnecting the positive cable. Make sure you don't have anything flammable around the bike. Spilt gas can ignite from arcing sparks when removing or installing battery cables. Lift out your old battery and take it to a battery or metal recycling center. The lead in the battery and the poly in the plastic can all be recycled. Battery lead is recycled more than any other industrial metal, and keeping the lead in your battery from leaching into local groundwater is an absolute necessity. Lead is a toxic metal, and it's harmful to people and animals. It can build up in your nervous system, causing permanent damage to your body. Before installing your new battery, take the time to clean the battery tray. Dirt or corrosion can find their way into the battery tray. Small rocks caught and wedged in the battery tray can also fracture the brand new battery case over time, requiring another complete replacement of the battery and possibly leaving you stranded. Ensure your replacement battery has the terminals in the correct position for your bike. Batteries come in a variety of configurations and sizes, and this includes terminal location. Most motorcycle batteries are between 8 and 12 amp hour. Some heavy cruiser bikes can have up to 14 amp hour batteries, while off-road bikes and older street motorcycles can have as little as 6 amp hour ratings. So what's an amp hour? It's a rating based on tests of the battery to determine how many amps the battery will deliver over a 1 hour period without dropping off voltage. 12 amp hours means 12 amps over 1 hour, and in the case of our 12-volt battery, this also means the current is consistent at 12 volts. When talking about amps, the question ultimately arises is how quickly can a battery be charged? Lead-acid batteries should ideally be charged at amperage rates of 10 to a maximum 20% of their amp-hour rating. So in the case of our 12 amp-hour battery, 1.2 to 2 amps from the charger is ideal. If you notice, the battery tender I use has a maximum amperage of 1.5 amps, so it fits nicely into that conventional charge window. The next question you're asking is, why can't I charge up my battery faster with more amperage? Well, the answer is heat. Turning up the amperage causes the electrolyte to boil. In the case of a flooded battery, the electrolyte, which consists of the hydrogen sulfide and water, boils away hydrogen and oxygen molecules, releasing them into the air. These gases are very flammable, so care needs to be taken, as a small amount of gassing is always occurring when charging or discharging a flooded battery. Now, in the case of a flooded battery where water can be replenished, a small amount of boil is okay. It's even desirable to assist in mixing the electrolyte and dissolving sulfate crystals. But by boiling a battery before it's fully charged also boils away the materials needed for the battery to do its job, and the battery never does reach full charge again. So by running too high in amperage, you damage the battery and it doesn't fully charge. In the case of a valve-regulated lead-acid battery, like a gel or AGM, applying too much amperage when charging can be catastrophic. The term valve-regulated battery refers to the gassing release valve in the battery top. Think of it as a safety valve, and should the battery in the bike malfunction, causing the electrolyte to heat up, it safely releases the gases instead of trying to contain them, like a soda bottle with a Mentos in it. The point of using a valve-regulated battery is that gases are not allowed to escape during normal use, trapping the hydrogen and oxygen in the battery case and glass mat so it can be reconstituted into the electrolyte when the battery is charged. If the safety valve is activated in a VRLA battery, a valve-regulated lead-acid battery, that battery is pretty much done for. The release of gases means the battery no longer has the chemical ingredients necessary to recharge. So although using too many amps to charge in your flooded lead-acid battery can be bad, too many amps in a gel or AGM battery is terminal. No pun intended there. Terminal, battery terminal. Anyways. When installing your battery, always ensure the main power lead from your motorcycle is the first lead on the battery terminal. Installing an accessory or battery tender lead between your motorcycle lead and the battery terminal can increase the amount of current resistance, and this resistance in the cable can result in heat and corrosion. The motorcycle is pulling the most amount of amps from your battery and should be the first one connected to the battery terminal. Ensure your accessory and battery tender leads are run so that they don't interfere with the panels or seat or anything else around them, and still be accessible to plug in when you need them. Use a little bit of dielectric grease on the contacts and the terminal to help protect them from moisture and corrosion. And that's pretty much it. Make sure the battery is secure with hold-down straps and whatever restraining mechanism your bike has. But other than that, changing the battery is one of the simplest things you can do.